Okay, welcome. We're going to continue in our discussion of AC electronics today. And today what we're going to be studying are capacitors, primarily capacitors in AC circuits, but we'll also discuss what a capacitor would do in a DC circuit just to get a better understanding of what a capacitor is. If we draw our attention to the board here, what I'm going to do is I'm going to draw the simplest form of a capacitive circuit, which would be a DC battery. So let's just say that we had a 12-volt DC supply. And a capacitor, by definition, is simply two conducting plates. So let's assume that my left hand here is a plate of aluminum. Okay? My right hand here is another plate of aluminum. If I take these two plates of aluminum and I separate them with some kind of an insulator, like air, okay, then this would constitute the most basic form of a capacitor. It's basically two conducting plates that are separated by something that's an insulator, and in this case, air. In the case of industry application, we usually don't find that we use air for a lot of reasons. We use things like ceramic or rubber or other things that can allow us to take the plates and push them against each other, but have something wedged in between that keeps them from shorting out. Because if I just had a plate and I put another plate on top of it, they would short out against each other. But if I had a plate and I put like some oil wax paper over the plate, and then I put another plate on top of that, there wouldn't be a short because there would be an insulator between the two plates. So let's take a look at what this looks like in the most basic form of a capacitor. What I'm going to show here is a switch that's currently in the open position, and then I'm going to draw in the top plate of my capacitor. So this would represent one plate with a given surface area. Okay, so let's just say that this is an aluminum plate, and then down here would be another plate, and then this plate is tied to the negative terminal of the battery. Now, when we buy these things from a supplier, okay, they come in what we call a neutral configuration, meaning that the two plates were at some point in time shorted out. And so generally when they manufacture these capacitors, they'll just take one lead and they'll just short to the other lead. And what that does is it causes both of these plates to be at the same voltage. Because if there's a short right here, right, then they're effectively at the same node. Okay, so there won't be a buildup of charge on either the top or the bottom. They'll be equal. Okay? And so for our purposes, if we just assume that we received the capacitor in an uncharged state, meaning that somebody had shorted it out before we bought it, then it would turn out that there would be an equal number of valence electrons on the top of the plate compared to the bottom of the plate. So I'll just draw the valence electrons as lowercase e's with little negative signs. So you notice here by my illustration, what I'm showing is a capacitor that has valence electrons, because any conductor obviously is made up of atoms, which has neutrons, protons, and electrons, and we call the outermost shell of electrons the what? Valence electrons. So all we're talking about here is the valence electrons, and the reason we're not dealing with other electrons or protons or neutrons is because they don't move. Right? In a conductor, like a piece of copper wire, we don't find that we have any movement of subatomic particles with the exception of valence electrons. Those are the only things that move. So that's what we're going to talk about here. So we have an equal number of valence electrons here and here. Okay? Now, the capacitor itself, which I'll just label as CAP, the capacitor itself, more than anything else, is an energy storage device. Okay, so let's just make a note of that. The capacitor is an energy The capacitor is an energy storage device. Very, very important, because capacitors in a large form, when they come like in the size of 50-gallon drums, can kill people. They can be extremely dangerous. So we have to treat them with a lot of respect, because capacitors can be very small and not dangerous at all. They can also be very large and lethal. Okay? But a capacitor is an energy storage device, and we're going to talk about the mechanics or the physics involved in how a capacitor stores energy. Okay? And then we'll talk about some of the characteristics of the capacitor. Now, in this circuit right here, let's just take note of the fact that we have an open right here at this switch. Okay? So we would expect that how many amps are going to flow through that open? 0. No amps at all. Okay? So if we go around this loop right here, what we find is we don't have a closed loop because there's an open switch right there. Right? Okay? So as a result, if we just came and we put a capacitor in here, okay, let's say we moved a capacitor from, a storage shelf onto this circuit, and we plugged it onto a proto board, okay, then if it were connected up to the negative terminal of a car battery, okay, and then over on the top side of the capacitor it was connected to an open switch, we would have no movement of electrons or no current flow. The only way we would be able to get current to flow would be if we close the switch, because then we would have a closed loop. So let's redraw our switch as a closed switch. So I'll just draw a straight line, which is really the same thing as a closed switch. Now we have kind of an interesting phenomenon that's occurring. Okay? If you take a look at this circuit right here, and you think in terms of the instant that that switch is closed, okay, what direction does current want to flow when it flows out of the battery? Flowing out of the negative terminal. So current, if we're talking about electron flow, not conventional current, if we're talking about electron flow, current wants to flow out of the negative terminal of the battery. Now, it turns out that if there's an equal number of valence electrons on the top and the bottom plates of the capacitor, and we were to come over and take a voltmeter, let's say that my fingers are the leads of a voltmeter, and we were to touch our voltmeter here and here before we close the switch, what voltage would we measure? 0. We'd measure 0 volts. If we were to come over here and touch a voltmeter between here and here, what voltage would we measure? 12 volts, right? We measure the battery voltage, 12 volts. So once we close the switch, now we have what's called a transient phenomenon. Something that's going to change real fast and then stop changing. Right? It's called a transient phenomenon. The reason is because we've got 12 volts across the battery, and at the instant that the switch closes, we've got 0 volts right here. Okay, well, I see a problem with Kerkoff's voltage law, because Kerkoff's voltage law tells us that the sum of the voltages around any closed loop must be equal to 0. Or stated more simply, if there's only two things in a closed loop, this voltage must be equal to this voltage. But we've already shown that if we came into the problem with a neutralized capacitor, a capacitor that was not charged, there would be 0 volts across it. So at the instant that the switch closes, the switch goes from an open position to a closed position. At the instant that that switch closes, we have 12 volts here and 0 volts here. Okay? And so things are not in equilibrium. Right? In other words, they're not balanced. And so nature, or physics, has a way of wanting to balance things out real quick. Okay? And so what happens is the following. What happens is current starts flowing. As soon as we close this switch, current starts flowing. Well, we know that the flow of current is the movement of valence electrons, right? Okay? So if current is flowing, and it's flowing in this direction, then where must it be getting electrons from? If we call this the top plate of the capacitor, and we call this the bottom plate of the capacitor. It's sucking them off the top. Exactly. What it's doing is it's taking valence electrons and it's sucking them off the top plate of the capacitor. As it sucks them off the top plate of the capacitor, those valence electrons flow as current through the battery and get deposited onto the bottom plate of the capacitor. At the very beginning, or at the instant that we close the switch, we get a flood of valence electrons. After a little bit of time has gone by, they start slowing down. Okay? Because in the very beginning, it's kind of like a big vacuum. And then we start filling that vacuum up, and the vacuum decreases, decreases, decreases to the point where there is no more vacuum. It's a situation like that. Okay, so after a period of time, all the valence electrons are going to have been sucked off the top plate of the capacitor and deposited on the bottom plate of the capacitor. Now, at that point, we would say that the system is in equilibrium. Okay? Now, in terms of measured voltage, what we would be saying when we say the system's in equilibrium is we would be saying that it now complies with Kerkoff's voltage law. In other words, this voltage is the same as this voltage. Okay? Almost the same. It's almost the same. The amount difference is very negligible, and we'll see what it is very shortly. Now, there is a graph that the book will throw out at you. And let me move over here and erase this. And this graph that the book throws out at you is a plot of time versus capacitor voltage. And if we move back to our circuit, we're talking about the voltage across the plates of the capacitor. Okay? So when the time was 0, in other words, the switch was still open, what did we say our voltage was? It was 0. So when we move back to our graph, that's a point on our graph right there. In other words, when the time is 0 seconds, okay, we have 0 volts across our capacitor. We assume that as time goes on, the starting point for time moving on is going to be the moment or the minute, the instant that we close that switch on the circuit. Okay? And we had a closed loop. Now, what we're going to do is we're going to talk just only about the voltage across the capacitor and how it changes with respect to time. And we're going to look at it two ways. The first way is the way that the book shows it to you. The book shows you that in a circuit where you have a capacitor that's hooked up to a DC power supply, let's say this is 12 volts, and this is 15 microfarads. That's the unit of energy storage that capacitance is measured in, is the farad. F-A-R-A-D, the farad. We already talked about the fact that when the switch is open, there's 0 volts. Okay? Once the switch is closed, the voltage across the capacitor starts to build up, and the reason that the voltage starts to increase is because the valence electrons that were at the top of the capacitor are now moving to the bottom side of the capacitor. So this electron moves down here. In reality, that would probably be billions of electrons. And this billion of electrons moves down here. And if we look at a plot of the voltage across the capacitor versus time, which we'll actually see on the oscilloscope in the lab, what we see is a graph that looks like this. We call that an exponential curve, or an exponential charging phenomenon. Okay, now, there's something that I'm going to show you here about this graph that you won't read in the book. And the reason that they don't give it to you in the book is because they don't expect you to understand logarithms, natural logs, calculus, and higher level math. So what they do is they just tell you that, well, this is how the voltage is going to build up with respect to time in a circuit where you have a DC source, a switch, and a capacitor. Okay? But let's take a look at this circuit right here. And if we were to apply Kerkoff's voltage law to this loop right here, the problem that we have in applying it the same way that we have in the DC study of this class is that it's not always the same. Remember, in DC, everything's always the same unless we change it, right? Okay? So Kerkoff's voltage law is analyzed using very simple algebra. Okay? When we have a situation like this, where we have an exponential buildup of voltage on the capacitor, we can still use Kerkoff's voltage law. It just turns out that we end up with this thing called a differential equation. Okay? And one of the prerequisites for this class is not differential equations. So all I'm going to do is I'm going to show you the solution to the differential equation. So if you were able to work out the differential equation, this is what it would look like. Okay? The voltage across the capacitor would be equal to whatever the voltage of the battery is. So we'll call this the total voltage, or our book likes to call that the total voltage. So whatever the total voltage is, multiplied by some fraction. Okay? The fraction is as follows. It's 1 minus e to the negative t over RC. Now, what in the world is this? This does not designate an electron, okay? What I'm doing right now. This is a mathematical equation, okay? The t in this formula right here is an exponent on this lowercase e. Does anybody know what the lowercase e represents? No, the lowercase e doesn't represent the number of electrons. In this case, it did. In this case, it's mathematical. It's the inverse of the natural logarithm. It's actually a button on your calculator. If you look on your calculator, you'll find a button that says e to the x. It looks like this. E to the x power. There's a button on your calculator that looks like that. Okay? And you usually don't have to deal with that too much until you get into slightly more advanced studies. But let's take a look at how we can use it. Has anybody found that button on their calculator? E to the x button? Okay. All right. Now, let's take a look at what the exponent is, because this is x. In other words, this x right here, that's this whole thing up here. Okay? So when we go inside the circle, the t represents time. The r represents the resistance of the wire in the circuit. So a lot of times people will draw it like this, just to lump all the resistance of the wire into one resistance. They'll draw their battery, 12 volts, and they'll draw a resistor in series with their capacitor. Time out. Just swallowed wrong or something. Okay. Yeah, we ready? Okay. So if we look at this circuit right here, really all it is the same circuit that we had before. All we've done is we have lumped the resistance of the wire into one resistor. And it might be a very small resistance. It might be 0.05 ohms. Okay? And then the capacitance, again, is going to be some number of farads or microfarads or millifarads or nanofarads or whatever. And I think that we said, what did we call this? 5 microfarads? 15. Oh, we had it 15? 15 microfarads. Okay. So back to our solution to Kerkoff's voltage law, or the solution to the differential equation. The voltage across the capacitor, which would be this voltage right here, okay, is equal to the battery voltage, which is this voltage right here, multiplied by a fraction. And the fraction is 1 minus e to the negative t, where t is how much time has gone by since we closed the switch. R is the resistance in the circuit, or the resistance of the wire. Okay? And then C is the capacitance in farads of the circuit. Now, what you can see if you look at this exponent right here by itself, and let's just look at this exponent here by itself for a moment. Let's take T over RC. If T represents time, okay, and I want this exponent to simplify into a really simple number, like 1, then what would T have to be equal to if this were going to simplify into 1? T would have to be capacitance times resistance. So in other words, if we were to substitute for the time the resistance times the capacitance, then wouldn't it be true that that would simplify into a 1? Because anything over itself is 1. So what we do, and what your book does, is it labels what we call the RC time constant. The RC time constant. And it'll say this hash mark right here is 1 times RC. This hash mark is 2 RC. This hash mark is 3 RC. And then 4 RC and 5 RC. Now, I'd like you to get your calculator out for a minute. Let me erase this. And what we're going to do is we're going to come up here to this exponent, and if we plug in 1 times RC, this whole exponent turns into a negative what? Negative 1. Exactly. So at this instant in time right here, this guy is a negative 1. Now, can anybody put in their calculator 1 minus e to the negative 1 power? when you put that into your calculator, you should get 0.632. 0.632. Okay? So basically what we're saying is that after one time constant has gone by, the voltage on the capacitor has built up to 63.2% of the battery voltage. We call that one time constant. 63.2%. Okay? And then there are others, which you can see in your book, and they'll tell you what they are for 2-time constants, 3-time constants, 4-time constants. But what I want to draw your attention to is 1-time constant and 5-time constants. So let's go back and let's put in a -5. What's 1 minus e to the -5? 1 minus e to the -5. .993. So what that tells you is that after 5 time constants, or 5 times RC, the voltage on the capacitor has built up to 99.3% of the battery voltage. We call that fully charged. That's an industry standard. So what we say is that 99.3, good enough. Once the battery voltage and the capacitor voltage are, or let me say it another way. Once the voltage across the capacitor is 99.3% of whatever the battery on the voltage on the battery is, then we say that the capacitor is fully charged. Okay? So even though you could say that, well, theoretically, doesn't this curve just keep going and going and going? Yes, it does. But as it keeps going, you're going to get 0.9993, and then 0.9999993, and then 0.9999, you know. So it becomes ridiculous, right? It becomes such a small number that it has no practical application. So we really stop to lose our practical application after what we call 5 time constants. Now the reason that I show you this is not because I'm going to test you on this, right? I'm not going to test you on math that I'm not going to expect you to know, but I want you to see where it comes from. In other words, this graph right here, we're not just pulling it out of the thin air. It's actually part of Kerkoff's voltage law, which creates or generates a differential equation, which this is the solution to. Okay? The book won't show you that. The only thing the book will show you is this, and if you really read it closely, you'll wonder where in the world did they get that graph. Okay? Now, what I want to re-emphasize here is that in a circuit where we have a DC supply that's hooked up to a capacitor with a small amount of resistance in it, and this capacitor is equal to some number of farads, and this is R, and this is your total voltage or your source voltage. If we plot the voltage drop across the capacitor versus time, we end up with a curve that looks like that. Okay? Now, in an AC circuit, this would represent what happens when the polarity is like this. But we know that in an AC circuit, the polarity is constantly changing. Okay? So in an AC circuit, when the polarity switches from positive negative to negative positive, and this goes away, then what we see is what we call the discharging cycle, which looks like that. So on our oscilloscope, what we'll see is a graph where it's charging and then discharging, and charging and then discharging. This right here is the charging cycle. And this right here is the discharging cycle. This is the charging cycle. This is the discharging cycle. Now, you might ask, so what? Okay, who cares? Well, one of the things that is really convenient about this and the fact that it always conforms to the same equation, even though it's an equation that we're not real familiar with, we can always predict when the voltage is going to be 63.2%, or when it's going to be 99.3%, or when it's going to be any value between those two. And so what that allows us to do is it allows us to create time delays in circuits. Okay? And creating time delays in circuits is a big part of designing interface boards or interface circuits for one system to communicate with another system. Okay? And we'll see exactly how to do that and why we have to have that in our next lecture. Okay? For tonight, does anybody have any questions about what a basic capacitor is or what the basic concept of charging and discharging a capacitor is? No questions? Okay, great. Everybody have a good night. Drive safely.